Hello everyone, this video will talk about another titration question, but let's see what this question about. Every time, right, when we into a titration question, we should, right, first thing first, recognize it. Is it strong as a strong base, strong as a weak base, or strong weak acid situation, right? So then let's look into that. Okay, so we have a hypochlorous acid. You go, we should know its chemical formula, but if you go, oh, I'm a little iffy, but in terms of solving this question, it's okay as you recognize this is a weak acid because its chemical formula should be HClO. Okay, it's a weak acid and titrating with a strong base. Okay, so then you go, okay, so it's a weak acid, strong base titration. Okay, so then that's first thing first, very good to know. And then also, I do like to draw the setup and then, help myself visualize it. Okay, so then since we have an acid, I say you have 25 ml, 0.150, so then that goes into the early mirror flask. Okay, so then we have 25 ml, 0.150 molar of this weak acid. Okay, and then in the early mirror flask, okay, so we have our strong base. Okay, so the strong base we have is sodium hydroxide. Concentration is 0.150, and then the question saying we're adding 13.3 ml of this strong base into my early flask. Okay, so then you go, oh, they're just adding, but remember when they're adding, there's a reaction happening. Okay, so then let's try to set that up. Okay, so we have the acid, which is HClO. Okay, reacting with the base. So this is an acid-base reaction. I'm producing salt and water. Okay, so then this is my reaction equation. There you go. That helps me to figure out after, right, I have my strong base into my early flask, then what happens, right? They react, apparently. So after the reaction, what do I still have? That's what we're trying to figure out, and then therefore be able to handle or analyze what's the, right, after the reaction, what's still there. That's going to help us to figure out what's the pH of the solution. And we have to know what it is. Then we'll be able to calculate pH. Okay, so then how can we recognize, right, what we're going to have? So then it's always good to recognize, is it before equivalence point, is it after equivalence point, or is it at equivalence point? Okay, so then again, what does equivalence mean? Equal amount, right? Equal moles of the acid and the base. Okay, so then clearly, good idea is we're gonna calculate the moles of the acid and most of the base, then do a comparison and see where are we at. Okay, so we have moles of the acid. That's easy to calculate since we're given with the concentration and the volume of it. Okay, so molarity is mole per liter times 25. Of course, we can handle the conversion. Okay, so this comes as 0.00375 moles of the acid. Okay, and then we can also calculate moles of the base. So moles of the sodium hydroxide, we're going to do the similar calculation. 150 times 13.3. 1 liter equals 1,000 ml. This gives me 0.00, about 2. Okay, of course, you can keep, right, the amount of appropriate amount of stick fix. Okay, so then I have, again, at this moment, I have more, right? Moles of this acid, I still have more, right? Has bigger than the moles of the base. So which means the pink, right, the base I added will be completely neutralized by the acid. I still have some leftover acid. Okay, so if that's the case, you will have leftover acid. Okay, so in here you have excess amount of, right, leftover acid still there. Okay, and then what else, right? So from this reaction, let's also show it from the work. And now how can we track how the reaction goes? We're gonna use moles, right? Okay, so we're gonna set up the mole information before the reaction happened, how it reacted is gonna according to the stoichiometric coefficients, and then after the reaction happens. Okay, so we already calculated. Start off with is this 0.0375 moles. The base we added was 0.002, and to begin with, we didn't have none of the product, so that's 0. Okay, and then again, for this reaction, we already analyzed, right? So you have less of the added strong base, so then that's limiting reagent. That'll be all reacted. We're gonna use the same amount of moles of the, we're gonna use all of the base. Okay, I'm sorry. Okay, and then we're gonna use the same amount of the acid. Okay, and then we're producing 1-to-1 ratio, since the stoichiometric coefficient from balance equation is 1-to-1-to-1-to-1. So after this reaction, I have none of the base left. This is all gone. And then we'll have more of the acid. How much is left? It's 0.00175 moles of this acid. Okay, so I already figured that out. And what else we have? We have this product, which is 0.00200 moles of this NaClO, and we know that's a salt, right? Okay, so how does salt behave? So you have that and salt. How does salt behave? Aqueous, which means soluble, so it's going to be 100% dissociated into ions. This is what? This is pH neutral because it's the compound of a strong base, so we don't need to concern about it. That's something we need to be concerned. So then let's see, we have weak acid, and with this species, you go, what's their relationship, right? You have a weak acid, let's label that, okay? So you have a weak acid with its conjugate base. You go, oh, I know what this is, right? Together, that's giving us a buffer. Okay, so then again, we recognize this is, right, you add a strong base, all neutralized before, right? Okay, and this is what? This is before equivalence point. So we're handling a situation for titration. This is before equivalence points. For strong weak situation, you actually have a buffer. Okay, so then you go, oh, I'm happy when I know I have a buffer, because in order to calculate pH of a buffer, I just need to use pK plus log of the concentration of the base over concentration of the acid. Okay, pK are given with Ka value. That's easy. So then let's do negative log of Ka value, which is 3 times 10 to the power negative 8 plus log base. Which one is the base? Right, look, that's the conjugate base, right? So that's the amount of base, that's the amount of the acid. As we also mentioned, since in Henderson-Hasselbalch equation, we're using a mole ratio and concentration ratio, and since they're in the same solution, so mole ratio equals to concentration ratio, so then we can just use mole ratio. Okay, so most of the base over most of the acid. Take a log of that, do the calculation. So the pH of this titration at this moment is actually pH of a buffer solution, which equal to 7.58. Okay, so then again, for titration, we really need to, right, use a mindset that this is an ongoing process. You have to analyze, right, after you add it, right, acid base, after they react, then what you have. So then that's what we're analyzing. Then in this case, before equivalence point, you actually have a, since now you have strong weak. If it's strong, that's a different story, right? This is strong weak, so before equivalence point, actually we have a buffer. Okay, so then if you recognize you have a buffer, then the job is very easy. Henderson-Hasselbalch equation will take care of the calculation. Then you will be able to do this, right? Okay, so then thank you for listening. Hopefully this is helpful.